section 1, minima and maxima, or maxima and minima, whatever. We are going to learn about functions now, and how to find these extreme values. So minimum and maximum could be present. They don't have to, but they could be present. And there are certain calculus methods that can be used to detect those values. Now we want to know min and max because they are related to maximum speed or minimum cost, maximum profit, maximum distance covered, and so on. So there's a lot of reasons why we do want to know where these points occur, especially for the models that are modeling situations that we encounter in engineering or whatever else we're doing. So let's take a look at first the names. So if I have a function that looks like this, some kind of f of x, we're going to have a maximum point here, and we're also going to have a maximum point here, and we're going to have some kind of minimum point right there. Now I'm going to put these arrows, and these arrows will mean that the graph is going to continue in that direction, in that fashion forever. So now, if you take a look at the first point, let's call it a f of a, because it is happening at x equals to a, and then we compute that in f. That one is going to be called the absolute maximum. It's the absolute max because it's absolutely highest point than the function reaches. And the one on the bottom is going to be called relative max, also known as local max. The one on top can also be called the global max. So we have those two. Absolute max and relative or local max. And we also have over here relative minimum, or also known as local minimum. Now the reason why it's local is because you will see that on this part of the line here and on this part of the line here, which is lower, right, you have lower points than the minimum. So that's why it cannot be absolute. While if you look at the max value, absolute max is the absolute max. If you look at some of those x cubed graphs that look like this, both of these are going to be local because there are lower and higher points. We don't have any absolute or global min and max in this situation. So both of these would be local. That's the local max, and this is the local min. You can also use the word relative. So that's the words, right? That's the vocabulary that we have to learn and use, and we have to and then label something as absolute min or the relative min or absolute max and the relative max. Now, these points, min and max, fall in a category of what we call critical points for the graph. And we're going to include one more type of a point later called inflection point. So these points, when you have a critical point could be min, max, or inflection point. And we'll talk about the inflection point later in next chapter or so, or next section or so. Right now we're only focusing on extreme values, which is min or a max. So the first the first thing, there we go, finally I said it. The first thing we're going to define is the theorem for extreme value theorem. So that's going to be the first theorem we're stating. We're not using it to compute anything, it's just something that shows the existence. And then we'll do calculations later. So theorem, which is extreme value theorem. So a function that is continuous on a closed interval, function, let's say f of x, that is continuous on a closed interval, a, b, both are x values, right? Has an absolute maximum value and an absolute minimum value on that interval. Has an absolute max and absolute min on that interval. I'm just going to draw a few cases so we understand this. So if I take, let's say, a parabola, but then we chop that parabola up, right? So let's say that's the parabola, and let's say it goes like this. So this value would be a, this value would be b. So that's the interval a and b on which the function exists. The two on top are both abs max, and the one on the bottom abs min. If you have a sine function 0 to 2 pi, clearly abs max and abs min. So anytime when you have this closed interval, you have a line segment, you are going to have min and a max. Can you have multiple? Sure, you can have multiple, because if you keep drawing the sine function, it's going to have as many as you draw. So they can have multiple absolute max and absolute mins flowing around. So what we want to do is we want to learn how to locate these values and to find min slash max. We find critical points. So to find these guys, we find critical points. So what is the critical point? So at the critical point, a f of a, well, no, sorry, x equals a. At the critical point, x equals a, the derivative is equal to 0 or does not exist. So that's how you get the critical values. And you see, if the derivative doesn't exist, then you might be hitting the vertical asymptote, which means that you're not going to have a critical point, but the critical value is still going to be there. And since it's asymptote, vertical asymptote, clearly you can't have a function value there. So that's also detected by this. So what does this mean? This means to find critical points, set the first derivative equal to 0, and also observe where derivative does not exist. So these are the rules. Now, for most part, students forget about this part, and then that creates a problem. I will immediately address this situation here. You see, if I draw a function f of x equals to absolute value of x, that function has a spike at 0, 0. Having a spike at 0, 0 means it's not differentiable at 0, 0. I said, when I said about the analysis, I said most of the time it's a vertical asymptote, but not always. So here is the case when derivative does not exist, right? Derivative doesn't exist at 0, but we do have a minimum there. So we have to be careful about these situations. So you are not only setting the first derivative equal to 0, you are also checking if the function has a point where the derivative is not defined. Now that happens mostly for vertical asymptotes, but then there are a few of these asymptote questions, the absolute value questions, and so on. Why does the derivative fail to exist at 0, 0? Because if you carefully look at the derivative, coming in from the left, the derivative is -1. Coming in from the right, the derivative is +1. So at point 0, 0, the point 0, 0 assumes the derivative -1 and +1 at the same time, and we can't have that. So if you are to graph the derivative for this, from the left, the derivative is like this, and you have to put open circle, and then you can close it on this side. It doesn't really matter which side you keep open, which side you keep closed. So you see that, and now this is y prime. So you see on the graph that there is this gap, and the derivative is trying to be both -1 and +1 at the same time, and that is not good. So we do have functions, just like absolute value of x, that are not differentiable at the point, and that is the reason why we have to include that in our procedure and make sure that we are detecting those as well. All right. Now, if nothing fishy is happening with the function, you have a polynomial, you have trig without asymptotes, so sines and cosines, you have e to the x, and so on. These functions don't have vertical asymptotes, and they're well behaved, which means that you should be able to find the min and the max fairly quickly. So how about y is equal to 3x squared? Well, to find either a min or a max, I know you know already what it is and where it is, but let's just pretend we don't. So the procedure calls for the derivative, which is 6x, and we set that equal to 0. We set that equal to 0 to figure out the critical numbers. So x is equal to 0 divided by 6, which is 0, and that is the critical number. So critical number. We can also compute the y value for it, and once you have x comma y, it becomes a point. So now f of 0 is 3 times 0 squared, which is 0. So now I have 0, 0, and that's critical point. So guys, points have x and y value, and the number is only on x. So when you compute the equation and you get something for x, that x is just critical number. It's a part of the critical point. Once you compute the y value for it, it becomes critical point. So, believe it or not, that's what it takes. Now, remember how many times you took the product rule, you took the chain rule, and I said factor, factor, factor? Well, here it is. This is why. Because every time you solve those derivatives now for chapter 3, you will be setting them equal to 0 to find where the critical points are. Once you know where the critical points are, you can do a lot for the graphing without the calculator and so on. Now the question here is whether this critical point is a min or a max. What is it? Min or max? Well, in our case, before we learn the tools of first derivative and the second derivative test, we can just sketch the function and see that it has a minimum, so it's a minimum. Right? We sketch the function. So it all depends on whether you know how to take the derivative and then solve the equation, or you don't. Functions that you know that do not contain any min or a max values should also, through this calculation, return that there are no critical points or min and max values. So you know that y equal e to the x has no min or a max because the function looks like this, right? It falls to the 0 on the left, but only at infinity, and it grows without a bound on the right-hand side. This function does not have any min or a max anywhere. Now, if you are to take the derivative here and do calculus on it, you see that this equation here has no solution. Which implies no crit points, which implies no min max. So let's take a few examples from the textbook. And it says, we'll do some of the spicier examples. So how about problem 29? It says f of x is equal to x over x squared plus 1. So are there any min or max values on this one? So take the derivative, use whatever witchcraft you have to take the derivative, and then set it equal to 0 and compute. Hello, welcome.
Yeah, I'll have to check that. Probably their website is not good.
Let's take a look at this. So which derivative we are using to, which method to take the derivative? Quotient rule. So we have x squared plus 1 squared. X squared plus 1 times the derivative in the numerator is 1 minus copy x, and then derivative is 2x. Awesome. So now we simplify this. We get x squared plus 1 minus 2x squared divided by x squared plus 1 squared. You will quickly catch up with the fact that you don't have to do anything with the denominator because it always gets cross multiplied into 0, so we don't have to bother with denominators. But numerators, we have to simplify, factor, do everything we can. In this case, we are left with 1 minus x squared, and then we have x squared plus 1, everything squared in denominator. And now we set this equal to 0 because we are looking for critical points. So at this point, as I said, when you cross multiply, 0 is going to annihilate denominator. You are left with 1 minus x squared equals to 0. That factors out into 1 minus x, 1 plus x equals to 0, from where we are calculating x is minus 1 and x is positive 1 as critical points, critical numbers. And now what we do is we find the y values for these two critical numbers by plugging these two critical numbers one at a time in the original function. So f of negative 1 is going to be negative 1 over negative 1 squared plus 1, which is negative 1/2. And f of 1 is positive 1 divided by positive 1 squared plus 1, which is positive 1/2. So critical numbers are -1, -1/2, and +1, +1/2. Now it's going to be difficult to say, because we still don't have the tools, whether these guys are min or a max. You can always use brute force. We are going to have an awesome tool coming up in next lecture called the first derivative test and the second derivative test, so we will definitely know what these are. Right now, you either know what the graph looks like, so you just say, okay, that's that minimum, that's that maximum, and so on. Or you do the very tedious calculation, which is based on the fact that if you have a max, right, and that's, let's say that's a -1 right there, you see that if you start computing -0.9, -0.8, negative, right, the value is going to start diminishing. So you know it's a max, because the values are getting smaller as you're moving away from it. And if it's a min, looks like that, right? And let's say that is at a value, doesn't matter, -1. As you are computing -0.9, -0.8, right, the values over here are going to rise. So if the values are rising, it's a minimum. If the values are getting smaller, there we go, then it's a min. So you can come up with a chart of values and observe what's happening with the y value and make a conclusion that way. But as I said, far more cooler, less tedious tool is coming up very soon. So let's take a look at -1, -1/2. So I'm going to just put a little chart of values here, and we can use the calculator to quickly compute. So I know that -1 gives me -1/2. I want to see what's happening with 0.9, -0.8, -0.7. That's plenty. You could have just used one value. So we use what I'm going to do is I'm going to quickly just put this function and graph it. So, and I'm just going to take a look at the table of values. So x divided by open parenthesis x squared plus 1. That's the function, if I remember well. Yep, x squared plus 1. And good. So now second table. Second table set. Table starts at -1, and the increments are 0.1. And then we draw Hey, I just started -1. Why? There we go. So for -0.1, I get -0.497. Then -0.488. And then -0.47, whatever. So observe what we got. I'm going to get rid of these pictures so they're not confusing. because they don't pertain to this problem. What I have here is the situation. I have at -1 is a half. No, sorry, -1 is a negative half. So this is where the point is. We know that point because we computed it, right? We can plot that. And then as you are going in, the value is going closer. So you see that that is a min. So that's why we are able to circle a minimum over here. Because these values are rising. You can only rise from a minimum. If it's a minimum, you can only rise. So if you see values rising, then that's definitely the minimum. If the values are diminishing, getting smaller, then it's a max. I always remember one aphorism from back in my country where it was really, really bad times economically and so on. The aphorism said, when are we finally going to hit the bottom of the barrel so we can actually bounce up, right? So it's, economy was really bad and no jobs. It's, was really, really bad at some time. So I will always remember that one and that way. All right, so we got this. And if you do the same calculation on the other side, there will be a point right there. And that one is going to get smaller like this. So the other one is going to end up working as a max. And if you don't trust me, don't believe me, just do the chart of values. But as I said, this is the tedious way of doing things, computing 1,000 points. The best thing is obviously to learn some kind of rule that you can just say, we apply this rule, min or a max, and be done. But that is after the test, right? Which is tomorrow. So there's one more thing left for this lecture, and that is to find absolute min and max on a closed interval. You will do the same thing like you did over here, and in addition to that, you will compute the endpoints. You will compute the y values for endpoints, A and B, that are given to you, because those could end up being absolute min or absolute max. So let's take a look at the absolute min max on closed interval. Now we had that theorem, right, which stated that if you have a closed interval, you must have min and a max. Throughout different books, it's worded differently. Maximum and minimum are attained and so on. There are many versions of that one. So first, let's think of the situation. So if you have a situation like this, clearly ABS max and ABS min. We don't care that this one over here is the relative right now because we're only looking for absolutes. We can do this, and you have the ABS max and ABS min. We can have a situation like this, in which case the endpoints are ABS max and ABS min. So you see, you have a situation where one of the endpoints and one of the points that is not endpoint are min and max. Situation where none of the endpoints are min and max, and situation where both of the endpoints are min and max. So it's not something that you memorize per function, obviously, because all different combinations that we can get. But you have to understand that these, the inside ones, are detected by the derivative procedure, and that does not exist procedure, where the ones on the outside, like these guys, are detected by computing the y value. Because once you find these through derivative, you will find their y values, and then you will simply say the highest of all y values is the absolute max. That should be common sense. And the lowest of all y values is going to be absolute min. So that should be all common sense. So let's take a look at two examples real quick. So easy one and then a spicy one, and we're done with this. So let's take a look at whatever. 24 is just fine for the first one. So f of x is given as 1/8 x cubed minus 1/2 x on interval -1 to 3. So at first, we are going to ignore the interval, and we're just going to find our derivative, set it equal to 0. So we have 3/8 x squared minus 1/2, set that equal to 0. Solve it. So we have 3/8 x squared is equal to 1/2. Multiply both sides by 8/3. We have x squared is equal to 4/3. We square root both sides. We get that the x is equal to plus minus 2 over root 3, and we rationalize. So plus minus 2 root 3 over 3. So this is what we have as our critical numbers. Now we plug them in the original equation to find y values for each one of these x's. There are two x's because of plus and minus. So f of 2 root 3 over 3 on the positive is going to be 1/8 times 2 root 3 over 3 cubed minus 1/2 of 2 root 3 over 3. So when you cube a 2, you get 8. So 8 and 2 will cancel actually. And you have root 3 cubed is 3 root 3 divided by 27 minus, these guys are gone, root 3 over 3. So 3 and 27 cancel. So you have root 3 over 9 minus 3 root 3 over 9, because we have to find the common denominator, works out to be -2 root 3 over 9. So we found our first critical point. The first critical point is 2 root 3 over 3 as x value, and -2 root 3 over 9 as the y value. So that there, critical number. We repeat the same calculation with a negative. So now we find f of -2 root 3 over 3, which is 1/8. And then you have -2 root 3 over 3, everything cubed, minus 1/2 times the -2 root 3 over 3. All right. So the negative will survive because it's a cube, right? You have 3 minus signs. But 2 and 8 still cancel because 2 cubed is 8. They cancel out. So you are left with -3 root 3 over 3. Remember, when you're cubing, let me just write it here. So cube root cubed is square root of 3 cubed is square root of 3 times square root of 3 times square root of 3. But these two guys give you 3, so that's why it's 3 root 3, if you missed that arithmetic for whatever reason. So we have -3 root 3 over 3. Those 3's will obviously cancel. The 2's cancel. Minus and minus gives us plus. Oh yes, it's over 27. It still cancels a little bit. Thank you. Plus root 3 over 3. So we have -root 3 over 9 plus 2 root 3 over 9. No, 3 root 3. And that gives us positive 2 root 3 over 9 as you compute. So now we have that the -2 root 3 over 3 gives us the value of 2 root 3 over 9. Also critical point. Wow, why did I write a number over here when it's a point? Much better. All right. The next step is to compute the function at the endpoints, because endpoints could be min and max as well. So I have the endpoints -1 and 3. So compute at -1 and then later compute at 3. So the function is 1/8 x cubed. So that's going to be 1/8 -1 cubed minus 1/2 times -1. This is going to be -1/8 plus 1/2, which is 4/8, so 3/8. 3/8. And we have for 3, so again 1/8, 3 cubed minus 1/2 times 3. So all we're doing is we're computing this at those points. 27/8 minus 3/2, so times 4 times 4. 27 minus 12 is 15/8. So we also have now two other critical points. There's a -1 3/8, and there's a +1 and 15/8. No, +3, not +1. +3. So those are also critical points. So now the list is -1 3/8, +3 and 15/8. Then we have -2√3/3, comma 2√3/9, and the +2√3/3 and -2√3/9 this way. So the lowest of all y values is absolute min. There is hopefully no questions about this one because it's the only negative number on the pile, right? It must be the smallest. And now is the fact just we need to compare 3/8 to 15/8 to 2√3/9 and realize that this one over here is the highest, right? Because that one is almost 2 when you compute. 16/8 is 2, and this is 15/8. So that's almost number 2. 3/8 is not even 1, not even a half. So that's definitely less than. And then 2√3/9, if you think about it, 2√3, you see, you don't have to compute every time if you are sufficiently clever about these things. You see that? You write 9 is 3 times 3, and you say 2 is smaller than 3, and √3 is smaller than 3, so that means this is smaller than that. If the numerator is smaller than the denominator, the fraction is smaller than 1. You can get the decimal if you're interested in, but so both first and third y values are smaller than 1, which leaves us that the one that's almost a 2 has the highest y value, which means that's where the absolute max is. And then the only negative number offered on a whole list is the one on the bottom, which means that must be absolute min. So you see that absolute max opens at the end, happens at the end point, and the absolute min happens somewhere within the function, between -1 and 3. So you try one example, and then we go for the break, and after that is the review and the lab. So what's interesting here? Here, this is an awful example, so you should be okay with it. X squared, square root of x plus 1 on -1 to 1. So x squared times the square root of x plus 1 on -1 to 1. what rule are we using for the derivative? Product rule. F prime of x is equal to, copy the first one, take derivative of the second one, and the chain rule is 1, so plus copy x plus 1 in the radical times 2x the derivative of the first. And now we have to clean this up. So it's algebra is the most annoying part of all of this here. So 2 square root of x plus 1 plus 2x square root of x plus 1. And then we are supposed to set this equal to 0 and solve this equation. Well, not a big deal, because we take one of these terms, move it to the other side, and cross multiply. So we have x squared over 2 square root of x plus 1 is equal to negative 2x square root of x plus 1. If you want to make your life easier, I don't know, if you don't see it, so you can put over 1. You don't have to. So now cross multiply, we get that the x squared is equal to negative 4x times x plus 1. Because square root times square root, it's a half plus a half, it's 1. And now we have x squared is equal to minus 4x squared minus 4x. Move everything to the other side. 5x squared minus 4x, no, sorry, plus 4x equal to 0. Factor out x, you get 5x plus 4. And then set each to 0. So x is 0 and x is negative 4/5. Critical numbers. We also have the endpoints that are given to us. The endpoints are, oh no, this problem did not have endpoints. Or it did. No, it did. Negative 1 and 1. All right. So compute for all of these. We need f of 0. We need f of negative 4/5. We need f of negative 1 and f of 1. We plug those in the original equation and just simply compute the values. So for 0, we get 0. Let's take care of the easy ones first. So for negative 1, I get 0 on the radical, so that's 0 as well. For positive 1, I get root 2. And negative 4/5 is the only one that has to be computed. So that's going to be negative 4/5 squared times the square root of negative 4/5 plus 1. So this is going to be 16 over 25 positive, because negative times negative is positive, and times the square root of 1/5. So the whole thing works out to be 16 over 25 times root 5, and then we rationalize because we don't like, right, square roots in denominators. So we have 16 root 5 divided by 125. So clearly zeros are the smallest values. So those are the mins, ABS min, ABS min. Crank the decimals for this and see which number is higher. Well, we can approximate square root of 2, right? That's approximately, oops. Square root of 2 is approximately 1.41. But I want to compute the other one, which is 16 root 5 divided by 125. Approximately 0.286. So square root of 2 is bigger, so that's our ABS max. And there you go. Ta-da! So I'm going to stop the stream and resume the stream for the review.